Welcome to enthalpy and phase changes. We know that a substance in the gaseous state has more energy than that same substance in its solid state. So that tells us that in terms of energy, gases have the most energy and solids have the least energy. So in order to change a solid into a liquid, or a liquid into a gas, you have to add that energy. And that energy that's added typically comes in the form of heat. So for the solid to liquid phase change and the liquid to gas phase change, these are clearly endothermic processes. And that implies that phase changes in the other direction, gases condensing to a liquid and liquids freezing to solid, that these must be exothermic changes. And we can also throw in sublimation and deposition. Sublimation is a solid becoming a gas directly, that has to be endothermic, and deposition being a gas going directly to the solid phase. So that's exothermic because it's going down in energy. So clearly heat is involved in these phase changes. The question is how much heat is needed for a phase change. Now to talk about a phase change, we have to be talking about a specific substance, because this question is going to be different for every substance. So for now, let's use water as an example of what happens to a substance as heat is added. Here we have what's called a heating curve for a substance. In this case, the heating curve is for water. A heating curve is generated by measuring the temperature of a substance as heat is added at a constant rate. So because this substance is water, there's a couple temperatures that are important to us. First of all, 100 degrees is right here, and 0 degrees is right here. Those we know to be the melting and boiling points of water. So that means in this area, the water is solid, because it's below 0. In this area, the water is liquid, because it's between 0 and 100. And above 100 is over here, where the water is a gas. So before we talk about phase changes, let's talk about where there is no phase change. We have this gas, liquid, and solid regions. Clearly there's a temperature change involved, because during these segments you can see the temperature is increasing. And because a temperature change is involved, we know that specific heat capacity must be involved somehow as well. And that the equation Q equals m times C times delta T is useful for figuring out how much heat is required for each of these temperature changes. But we've already talked about that in a previous video. So let's focus on these flat regions. And as you might predict, based on where we label the regions of solid, liquid, and gas, these flat regions represent the phase changes. In this larger flat region, we have H2O as a liquid becoming H2O as a gas. And in the lower segment, we have H2O as a solid becoming H2O as a liquid. And these phase changes have specific names. This top region, this top one, is called vaporization. And this bottom flat region, where the solid is melting to a liquid, we call that fusion. So this region down here is referred to as fusion, and this upper plateau is referred to as vaporization. Now a couple things to point out about these phase change areas, the vaporization and fusion plateaus. First of all, there's no temperature change. And what does that mean? It means that there's no change in kinetic energy. But that should be odd, because heat has been constantly added this whole time. So if heat is being constantly added, how come the temperature suddenly stops changing for a period of time? And that's because the heat is absorbed as potential energy. So during a phase change, there's no change in kinetic energy, but there is a change in potential energy. And that should make sense, because molecules in the gaseous state need to be further apart than molecules in the liquid state. Molecules in the liquid state need to be further apart than molecules in the solid state. And potential energy is the energy of position. So that's a major idea for this section, that phase changes involve a change in potential energy, but no change in kinetic energy. Now we're going to focus more on this heat part. We already know how to calculate the heat during a temperature change. For those regions where we have the solid, liquid, and gas heating up, we can use the equation Q equals m times C times delta T, the specific heat equation, to figure out how much heat is used for those temperature changes. But we also need a way of looking at how much heat is needed for the phase change, this fusion plateau and the vaporization plateau. And we clearly can't use a specific heat equation because there is no change in temperature. So let's take a closer look at those two regions. So here we have the reactions for fusion and vaporization. Both of these are endothermic processes, which means they both have positive heat of reactions. And we actually call the heat of reaction for these something special. For the solid water becoming liquid water, that's delta H fusion, the heat of fusion, and that is 6 kilojoules per mole. And for vaporization, it looks similar. We have delta H for the vaporization, the heat of vaporization, and that's equal to 40.8 kilojoules per mole. Now these values are specific for these reactions. So a substance other than water would have a different heat of fusion and a different heat of vaporization. So what do these heats of reaction tell us? Well, the heat of fusion tells us that it takes 6 kilojoules of heat to melt 1 mole of ice, and the heat of vaporization tells us it takes 40.8 kilojoules of energy to vaporize 1 mole of water. Now, sometimes it's useful to have information in terms of moles, but typically when we're melting something or vaporizing something, we know the mass of it. So it's going to be more convenient if we know the amount of energy per gram needed to do these phase changes. And the conversion is fairly simple if you just use the molar mass, but for these reactions, so for water, the heat of fusion is 334 joules per gram. So it takes 334 joules for every gram of water to melt. We have a similar value for the vaporization, in that the heat of vaporization, H sub V, becomes 2,260 joules per gram. So how do we use these constants HF and HV? Well, there are two very similar and very easy equations that show us how to use them. Q equals m times HF, and Q equals m times HV. These equations allow you to calculate the heat, Q, for a particular mass of a sample, given the amount of energy needed for the phase change. Let's take a look at an example that lets us use one of these equations. This question is asking how much heat is absorbed to completely melt 20 grams of ice at 0 degrees Celsius. The key term for this example is melt. That tells us that we're dealing with heat of fusion. So we want to use the equation Q equals m, mass, times the heat of fusion. The next thing I want to do is identify my variables. It's asking how much heat, so Q remains a variable. It also gives me the mass of the sample as 20 grams of ice, and the heat of fusion value depends on the substance itself. So for ice, for water, we said is 334 joules per gram. So now that I have my variables identified, I can go ahead and plug things in. So Q equals 20 grams times 334 joules per gram, which is equal to 6,680 joules. And that's the amount of heat needed to be absorbed to completely melt 20 grams of ice at 0 degrees Celsius. That wraps up our lesson on enthalpy and phase changes. Write down any questions you have in your notes and bring them with you to class.